Hello and welcome to my presentation. I hope you hear me well. And I'm Kuba Demianowski, and I will take you through the journey of probabilistic data structures. We'll outline how they are different from classical data structures, where we could find them, and when it's a good idea or not to use them. So, we'll go through the story of finding a customer and looking at the JVM heap. Based on the simple example, we'll see how probabilistic data structures are different than classical data structures. Also, we take a look at the JVM heap and see what are the differences between memory usage of different data structures. Let's start with a simple example. Let's start with this. Okay, I think that there were problems with audio, but I think that everything is solved. And yeah. Okay, so let's start with utilizing classical structures. I do not care about any technical issues. And what we should do at the beginning, if we would like to find a customer, we need to define our customer. For that, we use a Java language. We create a customer ID record with a simple field integer ID, and let's create 1 million of customers for our demo purposes. So we are taking a stream of integers. We are mapping to customer identifiers, and we are mapping to a list. And voila, our customer list is ready. And how could I know if the customer on the list exists? It's quite simple. While using a list and other data structures, usually you use method contains. Does it contain a new customer with identifier 100 or with customer with ID 80,000? 1,000, hundreds, whatever, or contains customer with ID -1 and a million. The answers are obvious. For the first two questions, the answer is true. This data structure is able to tell us if it exists or doesn't exist. Fairly simple. But let's take a look at the JVM heap. For that, I was using Visual VM, so free and open source tool for visualizing a Java heap. So a place where we store objects which are created during the runtime. And look at those two guys. We have our 1 million customer identifiers, and their size is 16 megabytes. It's like fairly enough. And also we have our list of n, and the size of it is 9 kilobytes, and the retained size is 20 megabytes. So let's see if we have one big list with huge retained size, and voila, you see it. And going further, let's see what is this magical retained size and why there's a difference between 16 megabytes and the list, which has 20 megabytes of retained size. So imagine that we have our customer list, which is pointing to our customer 1, customer 2, and customer n. So the shallow size, so applying size, is the size of only of a customer list. So only a data structure without the memory allocated for objects which are referenced, and the retained size is the size of a object and other objects which will be freed by the garbage collector once you remove the root object. So once we remove the customer list and then JVM, we also remove customer 1, customer 2, and customer n because they are no longer referenced. So that's what is retained size. So looking for this at the second time, we see that the retained size of our list, it's 20 megabytes. So we see that there's about 4 megabytes of overhead to store it. As most of you know, Java util immutable collection list is quite memory efficient collection. There's only one issue, time complexity O from n. In order to find an element on the list without knowing where it is, what's the index of it, we need to iterate over every element. The same like in linked list. To say that the element does not belong to a list, it takes us to see and visit each element. And let's think if we could do this better. I think that we could. Let's move to our Hashset. As all of you know, a Hashset, so it's a hash map where you could store values under a certain identifiers, hash keys. So let's reuse our customer and let's create our Hashset with customer identifiers. Let's generate 1 million of them, and let's move to using a Hashset new, using collectors to collection. And the API hasn't changed a lot. Still, we use method contains. It's quite fine that once we switch a collection, it does not switch an API. A customer with identifiers 100 and 100,000, they exist. With -1 and 8 million, it doesn't exist. It looks fine. The time complexity average is O from 1. As you probably know from data structures, once you have a collision in a hash set, so under a given bucket, under a given hashing key, you have more than one element, then you will have a red-black tree. That's how Hashset is implemented on the JVM. So the worst complexity, it's n, it's log from n, so we need to iterate over a red-black tree in terms of a collision. But what we saw there, oh my God, our customer identifiers, they took 16 megabytes, but our hash map is 56 megabytes, unfortunately. And as we see, there's a one huge hash map. So in order to store 16 megabytes of data, we need to occupy 56 megabytes on a JVM heap, because hash map is much more memory consuming data structure than an array. Also, as you know, hash map is not always filled with 100%. We need to have some free space to avoid collisions. So what we bought a speed of checking if the element exists. But what we received is a huge memory bill. I do not like that. So who could rescue us? A Bloom filter to the rescue. Bloom filter is a probabilistic data structure, the first one, which we will talk about. We could check and see if element does not exist. So that's great. We could see that the customer does not exist, and we could check if element may exist. So we could have a possible false positives. So a Bloom filter could told us this element, this guy exists in a customer list, but it could turn out that he does not exist. Fortunately, it will not lie when asking if something does not exist. If Bloom filter says that it doesn't exist for sure. And it's time for another example, another demo to implement an sample Bloom filter. I will use our old good friend Guava library provided by Google. And let's use our customer ID. Let's create a funnel. What is a funnel in Bloom filter? A funnel is something which helps you to map your object to an internal Bloom filter representation, which will be later used. How? I will explain it. And let's create our Bloom filter. So now let's do not focus on those magic parameters. Let's just feed it with data. So we will use put methods, and and check how does it look like on the heap. And oh my God, where are our customers? They are not present. We cannot see them. Is it good? Yes, it is good because we created them, fitted our bloom filter, and they are gone. Our JVM saw that they are no longer referenced, they're no longer needed, so Garbage Collector just thrown them away. And we are left with a one bloom filter with only 0.6 megabytes. So it's not a lot. You could also see at the bottom that we have a data and array with 7,400 items. That's actual length of our bloom filter. So let's try to use it. Let's see how it performs. Let's see the customer with identifier 100. It may exist. It's true. With 800,000, it's true. It may exist. Great. But customer with ID -1, it may exist. And the answer is true. It's false positive. Because no one has make a statement that there will be no false positive. They could be. The customer with identifier 8 million was correctly recognized as not existent. So what we could do with this? We could try to optimize custom parameters. So in data structures, usually apart from setting up and some like basic information, what we want to achieve, we want to also set some parameters. So in case of a bloom filter, we set the number of expected insertion to the constructed bloom filter. It's 1 million. It's fairly okay. We actually inserted 1 million elements, but this what we need to tune is the desired false positive probability. So the probability of false positives. So once we decrease it, we should have like much less false positives. That's one of the drawbacks of probabilistic data structures, that you need to know those numbers up front. And we change that, and the customer with identifier -1, it's false. Now it's okay, it doesn't exist. Great. The 8 million also doesn't exist. And how much do we pay for that? We paid for that by growing our bloom filter from 0.6 megabytes to 1.8 megabytes, roughly. And why is that? Because we had to make our bloom filter much wider. As you may see on the bottom, in our array, we have 2024 and 650 items. So now we need to store much more data. So another outcome, the more you would like your privacy data structure to be accurate, the more data it will consume. If you do not care about the quality of your data, you could still try to downsize it. Yeah, that's actual the screenshot from the previous example, when this false positive ratio was much smaller, and the array of data which is used by bloom filter was only 74 items and weighted around 0.6 megabytes. So how does it work? How the magic happens? Let's talk about it. Let's create some dummy example with empty bloom filter. A bloom filter is just an array of 0 and 1 values, which are on a position. There, of course, the length of the bloom filter could be adjusted. So let's add our customer and how to do this. In order to do this, we need some hashing functions. We'll use 3 hashing functions in this example. Usually in implementations, real-life implementations, you will see much higher number of hashing functions. And we calculate a hash function of our customer. So we have our hashes 930611113, and how to put it to our bloom filter. We need to use a modulo. So a modulo of hash and the length of our bloom filter. The length is 8. So a modulo from 940 and 8 is 1883. 3, and later it's 2. So it's time to update our Bloom filter. We marked position 1, 2, and 3 with 1s, and great, our first thing, our first customer is our Bloom filter. Let's add another customer with identifier 510. Let's calculate hashes once again, and also a side remark. Usually for hashing functions for probabilistic data structures, we use quite fast hashing functions, which are kind of different from secure hashing functions. So that's a side note. Let's calculate a modulo. A modulo is 206. So let's update our filter. At position 2 was set to 1, so there's nothing to change. Modulo from 0 was set to 0, so it will be updated to 1. And modulo from 6 also was 0, so we change it to 1. As you may see, once we are adding next, and more elements, the Bloom filter is getting green, more green, and more green. So as you see, to have a false positive ratio and higher accuracy, you need to make it bigger once you add more elements. Okay, so we inserted our data to our Bloom filter, and let's try to check it. How does it work once you would like to check it if the element exists? The same as with inserting the elements. So let's tackle the customer identifier 340. Let's calculate hashes. The modulo from our hashes is 237. And let's check the positions on our Bloom filter. It's position 2 is 1, position 3 is 1, but position 7 is 0. It's definitely not present. If it was present, for sure the Bloom filter array on position 7 will be filled with 1. So maybe check the customer with 730. Maybe this one exists. And let's calculate our modulo function 016. We check that, and the item may be present. It wasn't added, but as you see, you may saw some false positives, and that's how it works. So there's a question, like what we actually achieved, and what we are doing it. We achieve a very good space efficiency. So we are storing 60 megabytes of data using 1.5 megabytes. And we are able to serve quite accurately questions. Potentially, we could store unlimited amount of data, but with a limited accuracy, unfortunately. What we also achieved is a performance. We no longer need to go through the whole collection or take care about collisions in our hash set. We only need to calculate a couple of hashing functions, and that's all. And you could imagine that once you calculate the first hashing function and you see that this element certainly is not in a Bloom filter, you do not need to have to calculate other hashes. And what are the trade-offs? Because for sure there are some. There's no 100% accuracy when it comes to false positives. It will never be 100% accuracy, unfortunately. And that's the usual trade-off of probabilistic data structures. You will usually do not receive 100% accuracy in all of the ways, because we achieve 100% accuracy if we are saying that something doesn't exist. And also, we lose original data, so we cannot retrieve it. As you saw, they're no longer on the heap. And as you could imagine, it's much harder to debug such an application when you put something and it no longer exists. And as I mentioned, you bring additional complexity to your application. So the people, your colleagues with whom you are working, they also need to understand what is this Bloom filter. Everyone understands what is the difference between linked list, double linked list, hash map, and red black tree, but usually people do not do a deep dive to probabilistic data structures. And I think it's time to discover some more probabilistic data structures and see what the web has to offer to us. So the Bloom filter, which we discussed, it's a classical membership data structure. So we check if a given element exists, and Bloom filter could tell us that does it belong to the data set. And there's one quite a huge problem. Imagine that you are trying to create a Bloom filters and index in database, and you're adding things to a Bloom filter. We are adding, and this is great. You could add things to the Bloom filter, but what in case you would like to delete one row? Then you need to recreate the whole Bloom filter from the scratch. So you cannot delete elements. For that, you need to use counting Bloom filter. And counting Bloom filter could answer additional questions. So does it belong to a set? And also we could delete elements from a set and check, does the count of a given element be smaller than n? So nice, we could see and check the number of occurrences of things in our data structure. And also we have our Kuba filter, a much newer data structure, which is also telling us if something is belonging to a data set. We could delete elements from a set, and we have some limited counting. So we could count elements, but to some extent. And the Kuba filter is not so widespread in comparison to Bloom filter because it's much newer. And the advantages of Kuba filter, if you are looking at them, it's probably most use cases which will be more memory efficient and faster, just like that. So where could I find those membership functions in an URL? Because that's what is interesting us. We know the theory, but for sure we do not want to implement it from scratch. Let's take a look at Apache Spark. We have a Bloom filter in Apache Spark, which you receive for free. And there is a very nice feature because from Spark 3.0, Bloom filter is used out of the box in join optimization. In Spark 3.3.0, you need to turn this feature on, but it's from Spark 3.4.0, Bloom filter is used to pre-filter data before actually performing a join. And also, you could utilize Bloom filter while reading from Parquet files, and this was implemented in Spark 3.2.0. Also in Postgres, you could create indexes based on a Bloom filter, so you could create quite a memory efficient, space efficient index. And of course, in Redis, you could use Bloom filter. And what is more interesting, you could also use Kuba filter. That's great. Do you have any more fun data structures which are probabilistic? For sure I have. So let's move on. Also, there is also a membership function, Bloom filters in Cassandra. As you know, Cassandra stores data in sorted string files, and Cassandra under the hood is using Bloom filter to check if within a given file there is a key which you're looking for. And let's go through the cardinality. So counting the number of distinct elements in the input. It's quite useful feature which could save us a lot of time. For sure, you could switch your distinct to something else. So what are the data structures which support cardinality? You have linear counting, probabilistic counting, log-log, hyperlog-log, and hyperlog++. So usually once you go to any database and you would like to count a distinct number of customers, you could use count distinct. And that's something which could be used as a replacement when you would like to estimate and do not read all of the data. And you may ask me, where could I find them? Of course, in BigQuery. In BigQuery, this implementation of hyperlog++ using HLL underscore count function. And in PrestoDB also there's a hyperlog approx distinct function. And in Redis there's also a hyperlog log. And last but not least, Apache Spark also implements hyperlog plus data structure, which could be used under the well-known function approx count distinct. And let's go to another very interesting family of data structures. So find similar elements. Once you would like to find, for example, similar data set, the elements in a data set, we need to compare each and element probably using Jakub metrics. Once you switch to probabilistic data structures, we no longer to do this. We could use local sensitivity hashing, mean hashing, or sim hashing. Where could I find them? Where do I find those functions? Usually in Apache Spark, there's implementation of mean hash LSH algorithm. In Elasticsearch, we have mean hash token filter. In Solver, mean hash. And that's all. So if you would like to find similar elements, let's try to some mean hash algorithm. And last but not least, frequency. So count frequency of elements. So how many elements has we seen? Usually, it's this data structure is usually used under the hood in your real-time streaming engine. Usually, we are not using that as a developers. Usually, there are two probabilistic data structures. There's a count sketch and count mean sketch. And if you would like to use them, you could use Apache Spark, this count mean sketch, and also in Apache Beam sketch frequencies, and in Redis. But as I mentioned before, usually they are already implemented in your favorite streaming engine. Okay, so let's go through some good ideas. So the basic good idea is to use your probabilistic data structures which are already implemented in your database or in your data processing tools, or like Apache Spark. That's a usual way to go. If you need to use probabilistic data structures within your application, try to choose library which already provides them, like Wavel, like a rock solid library which is battle tested throughout the years. And also utilize tools which use probabilistic data structures under the hood without your knowledge. For example, Apache Spark from 3.4.0 has property Bloom filter enable set to true by default, and you will be pre-filtering your joins using Bloom filter and without knowing that. And also Google Dataflow utilize Bloom filter. And think twice if you want to implement probabilistic data structure from scratch, unless you're working on your own database or data processing engine. You want to use probabilistic data structure, but you must have exact results. For example, financial reporting, probably that's not the best idea. And you operate on a small data where probabilistic data structure will not introduce a significant performance memory optimization. So, and even if you are using probabilistic data structure and it's a valid case in your valid case, be aware that they could bring additional complexity to your code base and increase cognitive load while working with the code, unfortunately. And this, what we software engineers are trying to do, is to create such an amount of the lowest complexity as it is possible. Unfortunately, usually probabilistic data structures increase it. So if you want to learn more, there are two great books on that. There's an algorithm data structure, massive data sets books, and which contains quite a huge information on probabilistic data structures, and also probabilistic data structure algorithms for big data applications. And that's the end of my presentation. So thanks a lot for watching.